Okay, guys, so if you have done it already, if you could please get the material for the workshop from my GitHub account, which is here. Yeah? And if you have internet connection problems, we have several USBs here with the material. You can just ask Virgil, who is sitting here on the front row. Yeah, okay, cheers. Okay, so thank you very much for being here. I'm Matteo Fasiolo from the University of Bristol, and I'm going to teach this course together with Virgil Frisch from Électricité de France in Paris. And so here this course is an introduction to generalized additive models, and the first part of the session, the first hour and a half, will be kind of broad and hopefully not too boring for those of you who already use these kind of models. And then in the second part, we get to see some more interesting stuff, in particular gamless models and quantile GAMs. So I start with introducing GAM models. And so in the first thing is to show, kind of give a definition of what is an additive model. Then I will briefly introduce smooth effects. And then I will also talk about big data methods for GAM models. And then I will explain some diagnostics and model selection tools. And finally, we get to see how to use this method in MGCV and MGCV's R packages. So what is an additive model? We are in a standard regression context. So we have a response variable y and a set of covariates x. And in distributional regression, what we want to do typically is to find a good model for the conditional distribution of y given x. And the model is typically parameterized using a set of parameters, here theta 1 to theta q, which potentially might depend on our covariates. And in a Gaussian model, so the simplest example is a Gaussian model where the distribution of the response is a conditional Gaussian, where the mean is a function of the covariates, while the variance, sigma square, is fixed. So as I show here, we have some scatter plot data. We are modeling the mean as a smooth function of our covariate x. And down here you have the code for how you will fit such a model in MGCV. Okay, so here you see that the variance we are getting is kept fixed. So then in a generalized additive models, the distribution of the response is not necessarily Gaussian, obviously. But still in the first morning session, what we assume is that if we have p thetas, p parameters, only one will be modeled as a function of the covariates. And we call such a model an additive model because we assume that this parameter that we are modeling, mu, which is generally related at least to the expected value of x, of y given x, is modeled additively in the sense that we have a sum of some fairly general effects, fj's, of our covariates. And this can be fixed, random, or smooth effects parameterized by some regression coefficients betas. And this is transformed using the so-called link function. So a simple example is a Poisson GAM where the distribution of y given x is a Poisson with rate mu, which is also identical to the expected value and to the variance of y. And in this case, we will be using, for example, the log link function in order to assure that the sum, after transforming the sum of these effects, we get a positive rate. So in this case, for a Poisson model, we have that the relation between the mean and the variance is implied by the distribution. On the other hand, we can have, of course, have models where we have extra parameters for the scale, that is a variance, or the shape. So for example, we can have a scaled student GAM model where we are, the conditional distribution is a scaled student distribution. And we are modeling additively the expected value of y given x. And then we have a scale parameter determining the variance. And a shape parameter which controls the degrees of freedom. And then later in the second session, we will see models where we have multiple linear predictors, which means that we are modeling, for example, not only the mean, but also the variance of a Gaussian model. In the first session, we only see models with where we are modeling only one parameter or one parameter of the conditional density. So now we briefly introduce the main smooth effects, those that we will use in the exercises. So if you consider an additive model where we are modeling the expected value of y given x using a sum of two effects, and for example, the first could be a polynomial in the variable x1, and then we could have a nonlinear smooth effect of x2. So in the context of these models, we generally build these smooth effects using spline bases. So the smooth effect of a variable x2 is just a linear combination of some known basis functions times some regression coefficients that are unknown and need to be estimated. And then, just to set kind of the vocabulary, we call the sum of the effects the linear predictor because it's linear in the betas, in the regression coefficient, but typically not in the x's, in the covariates. So a simple example are B-splines. So these are a number of B-spline basis functions. So and they are just a shifted version of each other. And then to build our smooth effect, what we will do, we will use our betas to scale each of these functions, and then we take the linear combination just to get our total effect. And then we have, so the basic, another basic type of one-dimensional smooth is the one you get using cubic regression splines, which are built using this, as all other spline effects are built using this S constructor in MDCV. K determines the number of basis functions you're using, and here we're saying we're using basis cubic regression splines. Here on the left we have a typical one of the spline bases. Again, they are shifted version of each other. You scale them up with the coefficients and you get your total effect, which is the black line. And then the motivation kind of behind this kind of cubic regression spline basis is that they are related to the optimal solution to the problem shown here, where you're trying to minimize a sum of squares over your observations wise, but at the same time, you're also trying to minimize the integrated curvature of your estimated effect. And so this part is a kind of a goodness of fit, while the part on the right is trying to keep your effect as linear as possible. And the balance between the two is determined by this gamma, which is called the smoothing parameter. So as you increase lambda, this part will be more important, you get something more linear. Yeah? Then we have other basis function. Another useful one is the cyclic basis function, which is, so here you have one of the bases, then you have several of them. Again, you take linear combination, you get your total effect. And the property of this kind of smooth is that the effect and its first few derivatives will match at the two extremes. So the x on this end, so the effect of at x equals 0 will match the effect at x equals 1. And also its first derivative will match. Which means that this kind of effect is kind of useful when you are modeling some seasonal effect, where you want, for example, the effect on the 1st of January to be the same, of the same variable on the 31st of December. And then another type of univariate smooth that is useful is the adaptive smooth. And this, so here we have this classic acceleration data set. And what you have here is that the data is kind of flat, and then it has a big oscillation that goes flat again. And here you would like to have a smooth where you're penalize the kind of complexity or the curvature of this fit in a different way depending on where you are. So you would like to be able to allow for quite a lot of flexibility in the center, and you want to go kind of flat at the two extremes. And in fact, the purple line, which is the adaptive smoother, does that. That's the big oscillation, and then it goes flat here. Well, if you use another kind of basis like cubic regression splines, what they do is that they are also able to model this big change here, but then the kind of the curvature that they need to adapt to this, we kind of spill over to this side, and they have this kind of spurious wiggliness. Then, of course, we can generalize to multiple dimensions. So this is the default constructor you use in MGCV to get smooth in 1, 2, or any number of dimensions. So if you use this, the basis you will be using is the thin plate regression spline basis. And this is related to this kind of optimal, is related to the optimal solution to this problem, where again you have minimizing a sum of square, but now over a bidimensional or multidimensional function. And then your penalty is related to the integrated curvature. So these are part x, second derivatives. So the penalty is kind of integrating the total curvature you have in the x and z directions. And again, you have the smoothing parameter determining the balance. So the important thing to know here is that because you have a single smoothing parameter in front of this penalty, this kind of smoother will penalize wiggliness across x and across z in the same way. And that is why it's called an isotropic smooth, because it has the same penalty across the 2 or more dimensions. So this is a thin plate spline basis. The first few basis, so we have 15 basis functions. On the bottom right, you have the total estimated effect. So the first few basis functions are kind of simple. They're just hyperplanes. So just planes. And then they get more complex. And then you take a linear combination of these, and you get the total effect on the bottom right. So as I said, that these kind of thin plate spline smooth are good when you have, in general, isotropic smooth are useful when the 2 variables involved or more, they are in the same units, such as kilometers. But on the other hand, you are dealing with different units, then you're better off using a tensor product smooth, which you build using this TE constructor. And this is built as I show here. So essentially, to build, so if you have 2 covariates, Z and X, and you want to build a tensor product smooth of those, you will construct first the smooth with respect to Z, and assume that this is parameterized using its value as 6 points, which are these black points here. Then to build, this gives you your marginal basis. Then if you want to get your total 2D effect, what you will do, you will take each of these values and you will let them change with X. And this ends up constructing a 2-dimensional tensor product smooth basis. And the good thing about this is that then you will have not 1 penalty, but 2. One that penalizes the wiggliness across, the average wiggliness across the red lines. So this will penalize the wiggliness across X. And then you have another penalty penalizing the wiggliness across Z. So these kind of smooth they allow you to have a different amount of, to penalize, the wiggliness in a different way depending on each dimension. And then we can build this kind of tensor product smooth basis using any kind of, or almost any kind of marginal basis. So if you just call TE and say x1, x2, x3, then you will be constructed a tensor product smooth using three cubic regression spline basis. But otherwise, you can choose what kind of basis you want to use for the margins. So for example, you can say I want a tensor effect of 2 variables, x1, x2. I want to be using a cyclic smooth across x1 and a cubic regression spline across x2. And then you have to provide a vector of basis dimension, so the number of basis functions you want to use. And you can do even more complex stuff. So for example, you want to say I have an effect over longitude, latitude, and time. And what I want to do with this D argument, I say the first 2 dimensions go together and they build a 2-dimensional spatial effect, which will be based on the thin plate splines, which means this is going to be an isotropic smooth, which makes sense because these are the same units. So I'm going to build the isotropic smooth of these first 2 dimensions. And then I want to make that change across time. and I want to be using 20 basis function for this spatial effect, and 10 basis function across time. So this is essentially three-dimensional smooth. And then if you use the TE constructor, it will automatically contain, by construction, we contain the margins, so the basis for these marginal effects. If you instead want to fit the margins, the effects for these two variables, plus the interaction, then you have to use this TI kind of constructor, where you say, I want this margin, this other margin, and the interaction, right? And the difference is mainly in interpretation, and then also when you plot it, you will get to see the margin separately and then the interaction rather than just one two-dimensional function. And then the last type of smooth I think we see in the exercises are bifactor smooths. So these are useful when you want to have a smooth effect, which will be different depending on which value of a factor variable you're looking at. So for example, a subject. So if you use this first constructor with the bi argument, then you will make so that your effect will be different. The effect of the value of the variable x will be different depending on which, for example, subject you're looking at. But the intercept of these, let's say, mean model, for example, it will be the same. Well, on the other hand, if you use this other constructor which is, you get it by using this basis equal fs, this will also give you a smooth that is dependent on which factor level you're looking at, but then you will also have an intercept which depends on the factor, and this is constructed using random effects. And a further difference is that if you use the first constructor, each curve will come with its own smoothing parameters, which means that the smoothness of each curve can be widely different depending on the factor level. While in the second constructor, you're using a single smoothing parameters for all the curves. So if you expect that for example, that the complexity of the curve will change widely across subjects, then you should rather use the first constructor. And this is just a representation of that. So this is what you get if you have a factor with two levels and you're using this bi-factor constructor. So you see that this curve is for sure more complex than this one, and they are penalized in different ways. Also that they are both centered, so they have the same intercept. While instead, if you use this fs smooth, you have, for example, each curve comes with its own random effect for the intercept, so they can be shifted. And the smoothness of them should be kind of similar because they have the same penalty on wiggliness. Okay, then I want to say just something about how we fit these kind of models. So again, you can think of a smooth effect as a sum of some coefficient that need to be estimated times some basis which can be multidimensional. And then, at least in our approach to this, to determine the complexity of these effects, what we do is to say, we are going to choose a rank R, so the number of basis function that we use, which is large enough so that potentially we can have fairly complex effects and possibly overfitting. But then what we do is to put a penalty on the regression coefficient, which will shrink them towards zero, and which makes so that we control the wiggliness of the effects. And essentially, so the way we estimate the regression coefficient, the betas, is by penalizing, by minimizing the penalized likelihood, which is given by the likelihood, which is then a goodness of fit criterion, minus a complexity penalty. And this complexity penalty will depend on the smoothing parameters. As you increase those, the gammas, this part will become dominant with respect to the likelihood, and you're getting fits that are simpler and smoother. And then, so if you want to like a concrete example, if you are modeling, for example, the mean as a function of x, and you have a univariate and a bivariate effect, then you can think of this kind of penalty as having a first smoothing parameters, determining the weight of the curvature along x1, and the second smoothing parameter also determining the weight that will be given to the total curvature across the second effect. And the fitting framework is typically hierarchical, so you have to determine first the smoothing parameters, and this is, well, the most general way, at least in MGCV, of doing this is by maximizing the so-called Laplace approximate marginal likelihood. And this is an approximation to the likelihood of your data given the smoothing parameter, where essentially we have approximated this kind of integral where we are integrating out the regression coefficients. And then, so this is an outer kind of iteration trying to maximize this. And then for any value of gamma, what you will be doing, you will be estimating your regression coefficient by minimizing the penalized, maximizing the penalized log likelihood that I showed before. So at the top level with the smoothing parameter, you're actually determining whether you're in a regime where your effects are very smooth, like here, or they're very wiggly. And then for any value of the smoothing parameter, you're actually, by estimating the beta hats, then you're getting your actual fit. Okay, and then I just wanted to say something about the big data methods. So recall that this is the GAM, the additive model structure. So we are modeling something that is generally the expected value of y, given x, as a sum of effects, and we are transforming this using the inverse link function. And then the fitted value at any xi can be written as the dot product of xi times our regression coefficient. And x is obviously the design or model matrix. And this will have n rows, as many as your observation, and then we'll have a number of one column for each fixed effect, the a's here, and then also one column for each basis function of each effect. And so this matrix has essentially a number of columns depending on the number of parametric terms plus the number of basis function used for each effect. So the point being that when n is big, so you have a lot of observation, and maybe you have a lot of effects, each of them using a lot of basis function, what happens is that this matrix gets very big. And this leads to two problems. So the first is that if x is really big, it might be impossible to store it in memory. Second problem is that whenever you want to compute something involving x, such as x transpose x, this is going to take time. And the solution implemented by the BAM function in MGCV is that you never create the whole of x. You only work with its sub-blocks. And actually, you don't even store the sub-blocks. What you do is that whenever you need to do a computation that involves x, you frame that computation in terms of the blocks, and you will only create the blocks kind of on the fly whenever you need them to compute something. And then, of course, we can use parallelization whenever possible to speed up things. And the more recent kind of addition to MGCV has been this discretization, which can make things faster and save more memory. And the basic idea is just that even though the original x has n rows, we can often discretize without adding a significant statistical error using b, which is much lower than n rows. So we try to eliminate kind of duplicate rows or kind of to approximate rows that look very similar. And so in MGCV, you will use the BAM function to fit big data GAM models. And this has this extra argument, which is the discrete equal true, which makes you use this discretization I was mentioning. And the number of threads, so you can choose on how many threads, how many cores you want to be computing, you want to be fitting this model. And then before moving to the kind of practical part, I wanted to show some diagnostics, which you might want to use. So of course, when you are in a regression context, well, one very popular diagnostic is QQ plots. So here you are plotting the empirical quantiles of your residuals against the theoretical distribution assumed under your model. And so from this, obviously, you can detect skewness to the left, to the right, over dispersion, heavy tails, etc. So these kind of plots are kind of useful when you are choosing what kind of distribution should you be using for the conditional distribution of y, such as Poisson as against negative binomial. On the other hand, they are somewhat less useful when you're trying to find omitted variables or you want to determine whether you should be use a nonlinear effect or not. So for example, you have a simple example where so the expected value of y is quadratic in x. And then if you were fitting a linear regression model in this case, what you will get just this flat red regression line. So if you take the residual of this and you do a QQ plot, you will not see anything that looks strange because the QQ line falls between the confidence intervals. So if you want to diagnose these kind of problems, we'll see in the exercise that there are some other better approaches. So one is these conditional residual checks, which apply to this specific case. What you will do is, let's take our residuals, let's bin them depending on their value of x. So we divide them in a number of bins. Then I calculate the mean residual in each bin, and I get one of these black points. So here already you can see kind of that there is a nonlinear pattern in the mean residuals in each box. And then what we can do is to also simulate residuals from our model and use those to get some confidence intervals, so we can actually see whether a pattern, a strange pattern that we get on the mean residual is actually significant under the model. So the fact that you're using simulation then is fairly general. You can apply to pretty much any GAM. And then, okay, so recall then when we build a smooth effect, taking a linear combination of basis functions, and these regression coefficients, beta, they are being shrunk toward 0 by the smoothness penalty. And the fact that we are shrinking these parameters towards 0 means that even though on paper we are using k regression coefficients, actually we could say that we are using less because of this shrinkage. So a measure of the actual number of parameters you're using is the effective degrees of freedom, EDF, which is always lower than k. And in MGCV, the number of basis functions, for example, for 1D effects, the default is 10, but this is kind of arbitrary. So sometimes you would like to modify it, and but luckily it's not generally it's not necessary to get k. It's not important to choose kind of k exactly. The important is that you don't set it too low, because if you set it too low, you will be limiting kind of the maximum complexity of the effect you're fitting. So it's better to be wrong on the upper side. And there are some checks we can use to see whether k, the number of basis functions, is too low. One is to use to look at the conditional residual checks I was showing before. So if you see residual patterns, you might think, okay, maybe I should increase k because I'm not capturing something here. Sorry. Or you can use this check function. So this produces a number of outputs, but among other things, produces this table. So here, in each row, you have one of the smooth effect with respect to one of these variables. K is the number of basis functions you are using. EDF is the effective degrees of freedom. So what you should be looking for is, for example, here, you see that we are using the effective degrees of freedom is 8.6, and this is very close to 9, which is the number of basis function we are using. And this means that we have allowed 9 basis functions, and we are using kind of all of them, which means that we might be smoothing too much because we are not allowing for sufficient flexibility. So you should be looking for whether EDF is getting close to k prime. And then there is also p-values that you get from this, and these are calculated by simulation. And essentially these are checking whether, if you look at the residuals across this variable, for example, if you order the residual according to this variable, whether you have autocorrelation, in which case you might also think maybe I'm missing something. But overall, I would say more to rely on this fact, on EDF close to k prime, rather than on the p-values. And then, of course, another thing that you can do, you can say, okay, I'm going to try to increase K, and then I can look at one model selection criterion and see whether it improves. So in the exercise, I mainly use the archaic information criterion. So this is given by minus twice the log likelihood. And this is kind of course, a goodness of fit part of the criterion. And then you have twice EDF, the effective degrees of freedom, and this is kind of penalizing model complexity. And then, of course, if you believe in this criterion, in AIC, then if a model 1 has a lower AIC than model 2, then you should be inclined to choose model 1. And then, of course, when you have fitted a GAM model, which I call fit here, then you can call summary as in standard regression model, and then you can look at p-values, and those can help you as well to determine whether it should include an effect or not. Okay, so, all right, so in terms of software, you might have used MGCV, which is the recommended R package for fitting GAN models. But today, we use the MGCV's R package, which is an extension of MGCV, which adds a more kind of better method for plotting the estimated effects, and also many more methods for doing visual model checking. So I think it's kind of nice for a workshop like this. And but then, of course, most of the computation, all the model fitting is done by MGCV anyway. All right. So now I wanted to just go over a couple of very simple examples. And you should have or downloaded, or you got it with the USB, you got all the material, the workshop use R18 material. So now we'll go into this R demonstration 1 HTML file. So if you don't manage to see there on the screen what I'm looking at, you can just open this file and kind of follow. Yeah. So in MGCV, the main function for fitting GAM models is the GAM function. And today we'll be using this GAM-V function, which is essentially a wrapper provided by MGCVs around GAM. And this makes easier to get these kind of newer plots and diagnostics. So we'll be using the GAM-V function. Then, okay, here I have a simple example. We have an additive model with 4 covariates. So we have our response, y, which is a function of 4 effects. And on top of that, we have some normal noise. So here, what I'm doing here is not really important, it's just simulating some data from this. And then I fit a Gaussian GAM. I'm using GAM-V function from GCVs. And then I start with a model just with 4 linear effects of each covariate. Say family equal Gaussian, because I'm fitting a Gaussian model. I provide the data. And then there is, okay, this argument, AVs, what it does is, here I'm saying I want to be I've fitted the model. I want to simulate 50 vectors of residuals from my model, because then I'm going to use them for the residual checks. So having fitted the model, I plot it. So I say plot my model, and then I say all terms equal true, because by setting all terms equal true, I say that I want to be plotting also the parametric effects. Otherwise, you normally plot only the smooth effects. And in this case, this wouldn't plot anything, because we just have 4 parametric effects. And then I use print to make so that the output, the 4 effects, get printed on one page. So these are my effects with confidence intervals. And then, of course, okay, I might say, okay, should we use a nonlinear effect for any of these? For example, should I use a nonlinear effect for x0? And one way to look into this is to use this check1d function. So you say check1d on your model, and you say along which variable you want to be looking across. And then then I add this thing, which is a layer. So all functions starting with L underscore, they're all layers. And what this does what I showed before, that is, it bins our residual depending on their value of x0. It produces these black points, which are just the value of whatever function you have put in here. So in this case, just the mean of the residuals. And I'm plotting it here. So these are just our mean residuals in each box. They are the black points. And then with the simulation, I got these red confidence intervals. And there are these small black dots, which are kind of not really important, but they're just the mean of the residuals on each kind of simulated vector. So there will be 50 points on each of these vertical stripes. And are those that are used to actually get the confidence intervals. So if I look into this, I see that there is kind of a quadratic-like behavior. And so I might think, okay, maybe I should include the smooth effect for x naught. You can do something similar for x2, you will get a similar plot. So next, what I do is say, okay, I'm going to substitute my linear effect for x naught with a smooth with 10 basis functions. Same for x2. Everything else is just as before. If I repeat my check, now I see that my residuals, they don't show a clear pattern, and they fall well within the confidence intervals. And then, of course, if I want to, for example, compare this model I just fitted with the one I had before, I can use AIC. And then, also, if you want to look some more diagnostic, I use this check function on your fitted model. And what this does, it produces some diagnostics. So here we have QQ plot, histograms or residuals, etc. What matters is essentially this table here. And this is the table I was talking about before. So what you have here that you see on our smooth for x2 at most 9 degrees of freedom, and you're using 8.5. So in this case, you might wonder, even though the p-value is not significant, you might wonder whether you should be trying to increase k for this variable. And then, okay, I can plot my effects. And again, I say I want to plot them on one page. And then, of course, if you want to focus on a single effect, you use this select argument to say I want to be plotting the second smooth effect. And then, of course, you have the usual output. If you call summary on the model, you get p-values and then some other information. And then in terms of big data modeling, in MGCV, as I said, you use this BAM function. Here we use the BAM-V function, which is, again, a wrapper provided by MGCBs, which has somewhat better visualizations. So here I'm saying, okay, my data, y, is given by a function of, bivariate function of the two covariates x and z, plus I have some normal noise on top. So here I'm just simulating my data. And then here I'm plotting, this is the actual function. This is how the expected value of y changes with x and z. So this is essentially the effect we are trying to estimate if we fit a GAM model here. So I simulated 100,000 observations from this, so this is kind of the minimum number of observations where you start seeing some benefit from BAM, from these big data GAMs. So here I want to fit a model using BAM-V. And what I'm doing is I want a isotropic, so same penalty on smoothness across my two variables. And I want to be using 6 basis functions. And then I have some extra arguments. So with this A-GAM argument, so this is a list. And this is stuff that will be passed to GAM or BAM in this case. And here I'm saying pass the argument discrete equal true, because we want to use discretization. And I want the computation to happen on 2 threads. And then as before, I'm using AVs with nsim equal 50 to say I want to simulate residuals from my model, because then we use it for residual checks. Then if I plot my fit, this will plot the only effect we have, which is this one. And what we see here is that these, because we know the truth, this of course is very different from this. And then so assuming that we didn't know this, we want to see whether we are over smoothing. What we can do the same thing we did before, like again check 1D. We can check across, for example, a variable x. We want to bin our residuals and see how they change. And you see kind of a big nonlinear pattern. But otherwise, in general, when you're looking at 2D smooth, you can use some better methods, or when you're looking for interaction. And for example, you can use this check 2D function. So here you're saying, I want to check in 2 dimensions, and these are x and z. And then I want this function, the L-grid check 2D function. What it does, it's the same pretty much as we did in 1 dimension. We bin our residuals in one of these hexagons. We then calculate the mean of the residuals in each box. And then we standardize the mean residual in each box using the simulation that we got. Right? So when you get a plot like this, you should, and then this BW argument is just the width of the bins across x and y. And so when you get a plot like this, you should be looking for 2 things. One is whether you have some systematic pattern. So you have this area here where all the residuals are very positive, and here they're all negative. So it's kind of clear that you are missing something, that you are over smoothing. And second thing, because you are normalizing using simulation, if you believe your mean residuals to be at least approximately normal, you would expect that the scale here should be something between -2 and 2. And then, okay, so having seen this, we think, okay, we are over smoothing. And so we can refit. We refit our model, everything is as before, but I'm saying, okay, this time let's use 100 basis functions. I refit, I repeat my checks. And now I see that what you would like to see, that it's just kind of some random pattern, so there is nothing evident here, and the scale is very close to what you would expect, to something between 2 and -2. So the fit, this 2D effect I used above was a isotropic tensor thin plate smoothing plane. Okay, and so we had the same wiggliness penalty on x and z. By alternative, I can use this tensor product smooth here. So these will have. What you need to do here, you see k now is a vector, so you need to say I want to use 10 basis function for the x marginal smooth, and I want to use 10 also for the z, and then of course the total number of parameters you will be using is 100 because of the product of the two, and everything else is as before. Or alternatively, if you want to, instead of having fitting a single effect containing the marginal and the interaction, you can break it down using the TI constructor. So you want to say, I want to fit a marginal for x, which with 10 basis function, same for z, and then I want an interaction term, again with the same number of basis functions. And if you, and this is going to be a tensor interaction, so one smoothing parameter per dimension. And then, okay, if you fit this and then you plot it, what you can use, again, plot as before with a select argument to say I want to plot the two marginal effects, which are these. And then you can plot, again, using the select argument, the third effect, which is the interaction, right? So these are different interpretations from before, right? Because the tensor effect we saw before is essentially the sum of these plus these. While here you get a look directly at the interaction. And then an extra thing that we have in MGCV is this plot RGL function, which is kind of useful when you have this effect on multiple dimensions. So what you do is saying you use this SM function to say, take my model and extract the third smooth, which is the interaction I'm just showing up here. So we extract it, and then we plot it using plot RGL, and residual equal true will add just a kind of residuals. So these are, you can't see it, it doesn't appear in the HTML file, but you can try it there are several examples where we do this, and it's kind of nice, especially to see what is the uncertainty on the surface, which is very hard to see in 2 dimensions. And then, okay, when you do the exercises, there are a few extra things that appear only in few of them, so I don't think it's worth I go over here because you might not see them. One thing that you might encounter is, okay, how to use the offset. There is some exercise saying that you should use offset. So if you don't know what that is, you might look into this document that you have. Then the second thing is a little bit more how you use this SM function to extract a smooth effect and to add the layers to plots. Another thing is how you use the select equal true argument in GAM to do automatically variable selection. And the final thing is how you use this ID argument when you're defining in smooth, what is its purpose, right? So if you encounter this, you can look into this, or you can call me or Virgil, and we try to answer your questions. All right. So are there any questions about what I explained so far? Okay, so if not, we can move into the, so we have some 45 minutes, I think, to work on the exercise, which is quite good. So you should have this material. You have the exercises, so we start this exercise 1. Each exercise has a solution inside the solution folder. So if you get stuck, you can look into there and they can help you out. And then the exercises, so essentially we have 3 main exercises which are focused on electricity demand forecasting. So these are all with the real data. And yeah, now the description is, sorry. Yeah, so I just noticed there is an error here. So we have the exercise 3 actually is, I copied the text from the first one, but the exercise 3 is something where, is this one where we are doing individual electricity demand modeling. So exercise 3, just look down the exercise because it's wrong what is written in the description. So then we have these 3 main exercises, and everything you need to do this is either I talked about it or it's in those documents that I showed. Otherwise, I put in, because not everyone is interested in an electricity application, we have some further application like some environmental stuff, medical. And yeah, there is a brief description of each. So if you see terms that you don't know, like Markov random field, which I haven't covered, maybe you can ask me or you can do another exercise. Yeah?